Hello. I've been invited last week to give a talk to my old PhD group about my current job as intelligence engineer at Input Output Global, where I've been for almost 2 years now. And I must say I really had fun preparing this talk because it forced me to put into simple words what I'm currently doing and explain, I guess, what the two fields of technical intelligence and blockchain are. So I'm recording this video because I think it might have wider interest. So what is technical intelligence? When you hear this, you might think of maybe military intelligence or business intelligence, which I would say they both have some traits in common. I would say in general, intelligence is about gaining some sort of insight for a strategic advantage. And technical intelligence in particular, it's about gaining insights on technology. Let's say on technology, right? And it makes sense then to have a technical intelligence team in a tech sector and in a high growth tech sector, right? Like blockchain or AI or maybe biotech. These sectors where there's still a lot of science being produced and a lot of technology on top of that science. Typical outputs of a technical intelligence team could be to keep track of industry trends. Okay, so what new research and new technology is being done in the sector. What are competitors working on? Do they have products that overlap with ours? And conduct due diligence. More accurately, right? Technical due diligence. So due diligence in general is the process of the background checks that you do on someone before getting in business with them. Okay, maybe it's you want to have a partnership with them, or maybe you're considering acquiring them. You want to know even things like do the people have a criminal record, right? So that's all part of due diligence. In the case of technical intelligence, that is restricted basically to their tech level. So is the research, the scientific research they found on, is it sound? Is their code base clean? Does it respect good coding standards and so on? That, I guess, might sound fancy, but maybe a bit vague. So in practice, what is it I do? Well, in a nutshell, I write reports for executives on technical topics, right, in blockchain field. So to say, basically, my job is to save time to decision makers by informing them from the technical point of view, right, on some technologies or competitors and so on. This means that I do a lot of reading, documentation, papers. Differently than the academic setting, here the papers are usually read very not thoroughly. Okay, so I skim through the papers. I literally jump to conclusions. I do a lot of writing, of course. So mainly the reports that I write are usually of two types. Usually either it's a deep dive on some specific topic, or it's something that has a more wide breadth but goes shallower on the details. And then very important is actually talking to experts. So this job requires me to be a jack of all trades, which means I'm a master of none. So it's always important to find someone that knows more about me, about the topic, and get their feedback. And thankfully, this usually in IoG is very easy because the talent pool is really great. And finally, I do a bit of coding in the form usually of getting some data or doing some basic statistics, right, to maybe plot some charts, automate some tasks, that sort of stuff. The skill number one that's required for this job is manage time, and I mean that in two meanings. So manage my time. Okay, of course, I can't get stuck there. We work in a time box fashion, so every 2 weeks deliver a new report. This means there's no time yet to get stuck on a topic, but maybe more importantly, manage or maybe in this case respect the time of the readers would be a more appropriate choice of words, because they are usually very, very busy people, right? And they have to use this information I give them to take decisions. So if this is I was really stressing this in my talk because it was, I think, for the audience was of mostly academics, or anyways people that have experience with academics, right? Because there also you do a lot of writing, but there's a very specific structure to a scientific paper, and that is usually you first detail your assumptions, right? Then you make some reasoning, you make some arguments, you prove something in maths, or maybe you run some experiments, and then at the end you discuss the results. Here it's often the opposite. So like the discussion of the results, let's say that's the most interesting part, and that has to go first, usually in the form of an executive summary. So I always try to write what I called here impact first writing. What I mean with that is I always try to put first the actual bit of actionable information, and I try also, if possible, to write in a way that all the initial segments contain the most important information, so that if someone stops reading at any one point, they will have gotten at least the most important, and then they can, if they want further explanations, right, those are there, but they are later on. What is blockchain? Well, this, I guess, I do think it's a topic on which there's a lot of misinformation, mainly because of all the economic, the financial incentives behind it, and there's a lot of you will find, of course, a lot of divulgation material online, but it's often, I would say, very biased, because people have some financial interest in it, right? Some short definitions that you may find are things like, well, it's a digital money ledger, it's an append-only decentralized database, programmable money, distributed trust system, or tamper-proof digital records. I think all of these capture some aspect of it, but the way that I like to think about it is that a blockchain is a service where there is no operator behind the service that you must trust. Okay, and here by service, I mean it in the classical client-server sense. So, like if you are connecting to a web page, whoever's the server that is serving you the web page is providing you that service. If you send an email with Gmail, right, you connect via SMTP to their service, to their servers, and they provide you the service of delivering your email. In those cases, you need to trust that the operator will actually carry out the service as they promise, right? If you send an email, you have to trust that Gmail will actually deliver your email as they say they will. In a blockchain, you don't need this, so that's why it's often called trustless. All right, that's I think the key word, and this makes it, in my view, the ideal backend for some pretty specific use cases, I would say, such as financial transactions, which obviously is the main use case of blockchain nowadays. On top of that, I would say financial scripts, which basically I mean all of DeFi, right, decentralized finance. But then there are some non-financial applications that also would benefit from this trustless characteristic, right? Such as digital identity and online voting. These are, I would say, are still being worked on nowadays, but there is definitely a lot of work in this direction. If we want to be slightly more technical, we could say that the blockchain is a distributed computing system with permissionless consensus. I like here the word computing because it makes you think really, okay, this is a new model of computation. A new model of computation means that we need to also adapt our mental model, right, of how we think about computation. And that's why it can be challenging, I think, at first to understand what a blockchain actually is and what it does, right? We need a new model. So about the other words in the sentence, right? Distributed, permissionless, and consensus. Let's see what those mean. Distributed means that the service is, as I said first, right? It's not provided by one operator, but it's provided by a network of operators, and of which you don't need to trust any. And because of this, I like to think of it as an emergent phenomenon of the network. Okay. permissionless means that anyone can participate in this network, and that all the nodes are the same, right? There is no special node with special functionality. Like it could be, for example, in a hub and spoke architecture, right, where you have some centralized nodes that manage things. Here, and typically, okay, of course, I'm oversimplifying things, but let's say typically in a permissionless blockchain, okay, all nodes are have the same functionality. And finally, consensus. That means that the nodes are reaching an agreement on what happened, okay? Or in other words, there is some shared state that we all agree on. These concepts are not necessarily tied with blockchain. So there are distributed systems outside of blockchain that have some of these characteristics, okay? Torrents are permissionless, anyone can participate, but there is the nodes aren't reaching consensus on something. So yeah, they're permissionless, but they don't have consensus. Spark cluster, well, it's a permissioned distributed system for sure. It doesn't really technically satisfy the consensus definition, but I mean, you could say that all the nodes are working together for some common goal. So in some way, okay, there is some form of consensus. There is actual consensus in an actual permissioned network with consensus is Kafka when you configure it with Raft instead of the default Zookeeper. And yeah, and of course blockchain, as said, has both, right? Okay, so how does permissionless consensus actually work? Because this I think can be very counterintuitive in the beginning when you start to think about these things. If it's permissionless, anyone can join, but we are saying that we can reach consensus, so that the nodes reach an agreement on something, right? But if I am a node, how can I reach an agreement with other nodes that could be just anyone, right? Because it's permissionless. And that's I would say that the key point of let's say of how a blockchain achieves this trust, this characteristic, and it relies on the synergy of two basic building blocks, which is cryptography and mechanism design. So cryptography, it's used to authenticate statements, okay, such as the user is requesting to send this many tokens to this other user. Mechanism design, the way I explained it to again the public of mathematicians, many of which work on inverse problems. As I said, well, mechanism design is like inverse problems for game theory. Inverse problems in general is when you're trying to start. So often when you study, for example, maths or physics in a university, okay, when you're first approaching topics such as differential equations, you start with a clear definition of the problem, right? And you're trying to figure out the solution. But then in real life, what often happens is that you have, let's say, something that is a solution, maybe comes from a experimental measurement, right? And you're trying to figure out what are the rules, let's say, what are the root causes that could explain this thing that I know is true, right? And mechanism design, as I said, could be seen as inverse problems applied to game theory, in the sense that in game theory, you usually define the rules of a game and then you go out to find, for example, the Nash equilibrium. Here in mechanism design, you do the opposite. So you have a final state of the players that you would like to achieve, and that in the case of blockchain, the state would be that all the nodes are acting honestly and they're doing their job of validating the transactions and creating blocks. And then you ask, okay, what rules can I define that will have this desired outcome as the actual outcome? So it's basically defining a set of rules or incentives, right, to get that. Permissionless consensus protocols are mainly of two types. Okay, there is the original Nakamoto consensus, which was proposed by Satoshi Nakamoto in the Bitcoin white paper. And this in this, the truth is considered the longest chain. So I haven't mentioned this yet, but the word blockchain refers to the data structure of a blockchain network. The way it works is that users are submitting transaction requests right to the network, and the nodes are periodically collecting these transactions into blocks, which are basically, so a block is a collection of transactions. Each block that is produced from the network has a link, a pointer to the previous block, and in this sense you are creating a linked list of blocks. And in probabilistic, so in this type of consensus, you can theoretically have branches off of this chain, right? And the longest one is considered the truth, the actual state of the network. This achieves so-called probabilistic finality, which means that if you're sending transactions to a network using this type of consensus, such as Bitcoin or Cardano, for example, you only have let's say, as time goes on, you are more and more sure that your transaction is actually final, so it will not be reverted, it will be valid, let's say. And this probability goes down with time, but it's always a probability, okay? It's never a certainty. Even though in practice, it is, let's say, it's so low the probability, right, that it's not, it's basically a certainty. Still mathematically there is a difference. And this type of consensus is generally much more robust, and it never halts. Okay, this is the very nice thing. It's just, it always goes on. The other type of consensus is a Byzantine fault tolerant style, or BFT, and this is actually predates. So research on this type of consensus comes, as far as I know, from the 90s already. So it predates Bitcoins by almost 20 years. But in the blockchain world, it actually came later. Okay, so it was adopted later on. And in this type of consensus, nodes are basically continuously voting. They're exchanging votes with one another. And it allows to achieve deterministic finality, okay, which is, it's nice, right? It's because deterministic finality means, okay, once a transaction is accepted by the network and it's a block and it's considered final, that's it, it cannot be reverted. However, the drawback is that they are usually much more complex. They need certain assumptions. So, for example, they need always to assume that all the nodes will be able to deliver messages between them in a certain before a maximum latency. So that means there's an impossibility result. You cannot have a BFT consensus in a fully asynchronous network. And because of this added complexity, they can halt. So they can arrive at a state where the network is not able to produce blocks anymore, which means it cannot provide the service, right, of actually adding financial transactions. And this actually happens. I mean, this happens quite often. In both cases, we have the mechanism design part, right, where that basically tells. So as part of the consensus, honest nodes are allowed to assign themselves a reward, and that's what keeps them. That's what keeps the incentives aligned, and allows the network to function properly, to provide its service, right. So all this basically was a background, and to conclude, I wanted to actually give just a mention of what my actual work is on. So what are actually blockchain trends in 2024? Well, a big one, of course, is scaling. Blockchains, they pay for this trustless assumption. They pay by being, in general, slow and expensive to do computation on. So there's a lot of work being done on how can we move some of this computation off the chain, or some of the data that's on the chain, move it on some other chain, for example, and then produce some attestation the computation was done properly, and have only this attestation in the main chain. So we use the security of the main chain, but without loading it excessively, right? That would allow it to scale more. There's a lot of work being done on inter-blockchain communication, because by default all blockchains are siloed, right? They are yes, they are network, permission network, but they're each their own permissionless network. And usually solutions in this area, they require some type of let's say, a secondary network. So a network that sits in between networks and some nodes that are running clients of multiple blockchain. And that enables, to some extent, to have communication that is trustless, because that's the hard part, is to have communication between blockchains that doesn't break the trustless assumption. I would say another big trend is definitely selective disclosure and privacy chains. This specifically for the non-financial applications that I mentioned earlier, such as digital identity. There is a whole other sector of cryptography in the form of zero-knowledge proof, zero-knowledge snarks, and virtual machines that will allow to do things such as hold your private identity in a wallet, maybe for example, an application on your phone, and provide proofs that let's say that your identity satisfies certain attributes, for which it's a bit a technical way to say to prove things like that you are above, for example, 18 years old, or that you live in maybe in the European Union. Without this, so you are able with these with this cryptography, with this technology based on zero knowledge proofs, right? You're able to prove these things without disclosing, for example, what is your actual age, what is the actual country you live in. So that is something that there is having a lot of work and will enable non-financial applications. And then finally, restaking. So this is quite recent trend, I would say. There are solutions such as Eigenlayer and Babylon that allow you to create new blockchains that borrow the security from, in this case, from Ethereum and Bitcoin. And yeah, with that I'm done. Thanks for watching.